Okay, here we go. This is for Wednesday, February 16th. All right. Last lecture we talked about the principle of virtual work, right? This is going to be a very important part of our energy and variational methods as we start deriving elements through this principle, right? Where essentially all the principle is stating is that a particle is only in equilibrium if the work done by all the forces acting on the particle is zero after the particle moves through a virtual displacement, right? So it moves over 1 unit while all the forces that act on that particle, right, given that displacement, right, the work done by those forces has to all equal zero, right? Otherwise, we would not be in equilibrium. So we looked at, well, what does that mean if we look at a single particle versus a system of particles, right? Well, a system of particles, now we're going to have internal and external equilibrium, right? Or internal and external work that's done by a system of forces, right? The interconnecting forces. And so we separated the virtual work that is done by those systems separately. So the virtual work of external forces plus the virtual work of internal forces has to equal zero, right? And the cool thing about this is that it doesn't matter what system or what type of system you have, right? Or the nature of the system. It's valid for linear, nonlinear, elastic, and plastic behavior, okay? Principle of stationary, right, potential energy, or sometimes this is read as the principle of total stationary potential energy or stationary total potential energy. Okay, it's all the same, right? And what does Cook say about this? Well, among all admissible configurations of a conservative system, those that satisfy the equations of equilibrium make the potential energy stationaries with respect to admissible variations of displacement, right? So what's that saying? Well, it's just essentially saying the work done by internal and external forces, right, of a conservative system is in equilibrium, right, when the potential energy is stationary, right, or minimized, zero, right? So change in potential energy. Well, what the hell is a conservative system? That might help also. Well, conservative system essentially just means it's elastic, or, right, if the work done by internal forces and work done by external loads, are each independent of the path taken. Then it's a conservative system, right? What does that mean? Well, there's no energy loss, right? No loss of energy along the path. Really no change in load, right? Independent, okay? And so if we have a conservative systems, right, that satisfies the equations of equilibrium, will make the potential energy stationary with respect to admissible variations of displacement, right? Well, let's go back to our springs, right? Let's look back at our springs. Well, in our last system, we had springs that were attached to particles. Right? The particles are pushing on the springs are pushing on the particles. And if we looked at the change in work delta W sub S. Well, it's the virtual work of the springs. Right? Delta W sub S. Well, that's really equal to the negative of the internal work, right, of the system. Well, why is it negative? Well, that's because the forces, right, that are applied, right, the forces on the spring are in the opposite direction than the spring on the particle, right? So since forces on spring are in opposite direction. Right, so if we assume a conservative system elastic, really that virtual work of the springs is really equal to the change in strain energy, right? So our change in delta sub S, right, or the virtual work of the springs, which really comes from our internal, right, our virtual work of internal forces, delta W sub I. Well, if we have a conservative system that essentially says independent of the path, or essentially we have no loss of energy along the path, right? Things don't heat up, things don't make noise, right? Energy in is energy out, sort of thing. So if we have a conservative system, or what they'd call elastic, we would get that the change in the virtual work of the springs is really the change in the internal strain energy in the system, right? Change in the internal strain energy in the system, right? What we call delta big U. Well, if we go back to our principle of virtual work, right, we had delta W sub I, or internal work, or the work done by internal forces, plus the work done by external forces equals 0. Well, now if we look at the change in sign, we can now say that our change in total potential energy equals the change in internal strain energy, right? Capital U. You guys are going to make fun of me for my U's, I know. Minus, because we have our change in sign, the work of external forces, right? And that all equals 0. So we have our strain energy. And we have our work of external forces. All right. I guess one thing to look at this as, or relate it back to, right? Our external forces, like, they do work, right? Or does work. So we are losing potential. Right? Our strain energy, right? Those internal forces are creating strain energy, right? Or potential energy inside the system. Right? So we have positive. So that internal, that increase in potential energy in, right? Subtracting the work done by the external forces has to equal 0, right? Or if we looked at it on a larger scale, right? Complete, or consider capital pi, which is what we would call our total potential energy equals capital U minus, right, capital W. This is our elastic strain energy. This is our work of external forces. All right. Well, we know that based on our derivation here, right? We took one spring out of a system of springs. Well, that system of springs is always different, right? Depending on the case that we have, right? Our configuration of the system, right? All those springs could be organized in different situations, different orientations, right? So really our total potential energy, right, capital pi, is a function of the configuration of the system. So really our total potential energy is a function, in this case, of displacement. And really, our total potential energy is the potential energy functional, right? Its primary variable is the displacement, U, right? But that could be a function of the function of x, right? The displacement with respect to x, the derivative of the displacement, right? A function of a function, right? An integral, you can imagine if we're looking at a surface or over a distance, right? We're going to be looking at, well, what's the total potential energy over a given length? Well, in order to do that, right, we're going to do an integral. And when we do an integral, we want to minimize that, right? Make sure that we're in equilibrium, right? We're going to minimize a functional or minimize an integral, right? So if we add some, right, if we look at the potential energy, knowing that it's a function of the displacement, right, U, if we add to U some small virtual displacement, we're going to call it delta U, our displacement with respect to x now becomes, right, the displacement with respect to x plus some small admissible virtual displacement, right, delta U sub x. And if we look at that with respect to what happens to the total potential energy, right, potential energy now becomes, well, we had the total potential energy, it is a function of U. So now we get pi with respect to U plus now delta U really equals pi plus delta pi, right? Essentially, right, we had some initial potential energy. We go through some displacement, virtual displacement. We're going to have some change in potential energy, right? And our principle of stationary potential energy states that delta pi, as you can imagine, right, is 0 when the system is in equilibrium. Right? It doesn't want to move anymore, right? So the change in its potential is going to be 0, right? Because it doesn't want to move anymore. What are these, right, admissible virtual displacements, or what is this small? Well, it's got to be physically possible. Right? This function has to be continuous. And it also has to satisfy displacement boundary conditions. Well, let's look at an example. Okay, we're going to do a simple spring example. Right, so if we look at a spring, okay, it's connected at one end to a fixed support. All right, other end to some node. That node has some sort of applied load P. We're going to say our coordinates X is off to the right, and we want to find displacement of a spring. Okay. Well, I think all of you understand this would be fairly simple, right? Spring, linear spring, force times displacement. Well, let's prove that that's the case using our principle of stationary potential energy, okay? So if we consider this as a conservative system, right? Energy in is energy out sort of thing, right? We can say that from above, we know that the total potential energy equals the strain energy added to the system. It's a terrible U. I'm terrible at capital U's. U minus, right, our work. And so we've got our equation. Our total potential energy equals the elastic strain energy minus the work of external forces. So U being our, I really don't like the way I write capital U's, U's strain energy that's really, right, internal energy into a spring. Well, if we look at that, right, force displacement curve, well, our force displacement curve, well, if we're looking for a linear spring, right, something like that, our energy that's in our system, if you remember from mechanics of materials, and you have our force or stress strain diagrams, right, which we'll talk about in a little bit, right? The energy absorbed or energy contained within the system is the energy underneath the curve. So for this spring, for instance, if we went to some force F, right, and some displacement delta, the energy contained by that spring is really the area under the curve, or 1/2 F delta. Well, we know that the force in this spring, being in a linear spring, is the spring constant times delta. Well, that means that our strain energy, therefore, our strain energy equals 1/2 K delta squared, right? So that's our strain energy absorbed into the system. Our work, right, force times distance, is just that, right? Force times delta in this case, right? We went to a force in the spring of F and we went to a delta, or that force that we applied was really P, right, from our free body diagram there at the beginning in our example. So we know we have an expression now for the strain energy. We have an expression for the work, right? Well, we know that once we apply a virtual displacement, right, delta U, we want to minimize that. We'll do the first variation. So let's give this system a virtual displacement. Let's go back and let's say, okay, we've got our support. We've got our spring. It's fixed on one end. Apply a force P. That force, I'm going to fix this. I've got to allow it to undergo some sort of virtual displacement, right? Due to some force P. That virtual displacement, we're going to call as delta U. Well, now our strain energy, knowing we have our expression for strain energy, is U equals 1/2 K delta. Well, delta is now our original delta plus some sort of delta, right? Some small arbitrary displacement. I'm going to square that. Well, now we get 1/2 delta squared plus K delta plus 1/2, right? K delta U squared. Well, if you take a really small value, right? This is a very small virtual displacement, a small increment. If that is small, we're going to make that go away. This is now equal to big U. This is really our little u, delta U. Right? Well, if we look at our work now, external forces, well, we have P times delta plus P times little delta, right? So this is our big W, and this is going to be our delta W. From up above, we really want to take the first variation, or really looking at what is the small incremental displacement due to the system overall. And when we set that small variation to 0, that means the system is going to be in equilibrium. So if we wanted to know the displacement of the spring given an applied load P, right, we would want to know the point at which a change in displacement in the spring, a very small one, would go to 0, right, with respect to its potential energy. So what does that mean? Well, that means I'm going to take delta pi, right, and delta U plus delta W, right, equals 0, because we're really setting the change in potential energy, or, right, the first variation equal to 0. And this is how we find our extrema, right, or our optimum path. What does that mean when we plug everything in? Well, our delta U, right, is really our K delta U. Oops, sorry. K delta minus P delta, right? That small displacement. Well, if we factor out our delta, we get K delta minus P. Now we have our small arbitrary, right? This is arbitrary. If it's arbitrary, we're just going to pull it out, right? Doesn't mean much to us. It's an arbitrary amount that we applied in order to solve. So really what we want is, right, K delta minus P must equal 0. Well, that means that K delta equals P, right? This is really our equilibrium of a spring. Or if we want to know the displacement of the spring, well, it's the load divided by our spring constant, right? And so we were able to solve for the displacement in the spring given an amount of load, knowing that if we took the first variation, right, or the change in potential energy, right, at some arbitrary or some small displacement value, right, if we set that equal to 0, because when we are in equilibrium, it will be 0, right, then we were able to obtain the equation for the equilibrium of the spring. We can review a little bit here, right? The principle of virtual work of a particle says that the particle is only in equilibrium when the work on our particle is 0, right, of the forces acting on that particle. Well, same happens for, right, the change in work external plus the change in work internal must equal 0 if we look at a system of particles, right, that are interconnected. So we have some internal and external energies associated with that. Well, the principle of stationary potential energy works further on that by saying, okay, right, our change in potential energy has to equal 0. And that means that our strain energy, change in strain energy minus the change in work, right, must equal 0. And we went through our spring example just now that said that our, right, principle of stationary potential energy, right, lambda, and we got that, or sorry, not lambda, pi, 1/2 k delta squared minus p delta. And in order to find our stationary condition, or really equilibrium, right? In order to find that condition, we set our first variation equal to 0. Well, that equaled k delta p delta u, or sorry, delta delta, right? This small amount, well, that's arbitrary. We're going to just say bye-bye to that, and we end up with our p over k, right? It's arbitrary in that it's not associated with the solution, right? It's just some arbitrary amount, and everything else needs to be set to 0, right? The k delta minus p must equal to 0 in order to get a 0 variation, right? Because that is an arbitrary displacement. So for systems with many, right, but they have to be finite degrees of freedom, we just run through looking at, one, right, the change in our potential energy with respect to, right, this change in displacement of the first degree of freedom, right, or change in our first degree of freedom, right? And we just add up all of the contributions from all of our degrees of freedom, right? d2 times delta d2 would be some small amount of virtual displacement of each of our degrees of freedom, all the way out to, right, the change in potential energy with respect to some nth arbitrary degree of freedom, right? And all of those must equal 0. So we had this net, right? We were looking at a single particle here. If we had this net, multiple particles like we do here, back here, right? Each of those particles, in order for the system to be in equilibrium, all of those, right, have to add up to 0. All right, so that is potential energy, internal strain energy. We are going to go to, bummer. I should have it did not update. Well, lucky for you guys, I guess we're half an hour deep. I'm going to fix these notes breakdown. We should have a variational bar element and beam element. I should have some skeleton notes. I already posted them up on D2L. I'll get organized here, and we are going to do one last, I'll have to get one last note or lecture together here when we start into the variational bar element. Here's the completed ones, which I don't want to do. There should be some skeleton ones in this folder that are not there, which is scaring me. So I'm going to spend a little bit of time here in the next day or so and get that organized. And then you'll have a lecture for Friday. Hope you guys are enjoying the week. Don't forget, email me if you have any questions about anything. I think I'll post the potential energy homework at some point this week. It won't be due till either the end of next week or maybe even the week after that. So anyway, yeah, reach out if you have any questions. Take care.